Okay, y'all, let's get started. I have to cancel office hours today because I have a cold, and my voice may seem a little hoarse, same reason. Hopefully, can get through the class because I'm going back to back. But fortunately, today's a pretty easy class, so we'll probably make pretty fast progress. I did want to point out that starting today, you have quizzes afterwards, and fortunately, the course has on Canvas a course calendar. So you can see there should be, why is this data modeling? There is no data modeling quiz. I have no idea why this thing is being, this isn't showing up actually for you, is it, on the calendar? It's just showing up for me, right?
Yeah.
Good. So you and I are looking at two different calendars, I'm afraid. So on your calendar, are you seeing that there's a quiz called, let's see, there should be one on the relational model. Let's make sure about that. Are you all seeing a calendar item saying relational model or not?
Yes. Yeah.
Okay, so starting today, there are quizzes, short ones there. You're given 20 minutes, and you have, they're due, the Tuesday ones are due Thursday, the Thursday ones are due Tuesday, right before class. Don't forget to do them. I'm not going to keep reminding you about it, okay? Starting today, you got to remember to do those quizzes. They are great preparation for the midterm. This many students, I have to basically ask multiple choice midterms. So guess where I like to take some material from? The quizzes. So the quizzes help you get ready for the midterm. Plus, remember, you have to do the before class assignments, okay? So with that out of the way, let's take a look at what we'll be covering today, which is essentially the theoretical basis for the relational model. So there's remember I said that there's two kinds of languages, the data description language and the data manipulation language. The data description language is like the variable declaration part of your program. It's where you specify the types of your variables, the names and the like. And the data manipulation is where you do your actual manipulation operations on the database. Today, we're going to be talking about the theoretical basis for the data definition language. Okay, for how relational database models are structured. Okay, then on Thursday, we actually get directly into doing the manipulation language. Then after that, we'll go into the theoretical basis for the manipulation language. I think it's actually, in order to understand how you're doing the manipulation language, you have to understand the basics of the relational model. So we do this first. Then we do the manipulation language, then it's theoretical basis. You all got, I hope, email telling you that you have a MySQL database. Good. Hopefully, one of the things you probably should do is change the password, lest you forget that password. And if you look at my SQL notes, getting started with your MySQL database, it tells you how to do that. Very simple, okay? So it tells you how to access the interpreter, blah, blah, blah. All under getting started. But that's for Thursday. That's not for today, okay? Also, actually, before I forget, on Canvas, under modules, I now have some additional material up, like Chapter 6 homework.pdf is where you find the homework problems for this first homework. So you'll sometimes see pointers to things. This is where those pointers end up under course materials. Okay. Back to this. Okay, so relations. They're very simple. They look like tables in a spreadsheet. The columns are attributes. The rows are what are called tuples or records. So here, this is from the property home management case study that most of the slides are based on. We're assuming that our property management company has multiple branches. By the way, the authors of this textbook were Irish, hence London, Aberdeen, Glasgow, rather than Knoxville, Chattanooga. So at any rate, we have a branch relation. It's a table. It has 4 attributes for the branch number, the street, the city, and the postal code. Then each row is a record or a tuple. We call it a tuple if we're using the theoretical thing, and we use the word attributes again if we're doing the using the theoretical jargon. The number of tuples or rows is referred to as the cardinality. So in this case, the cardinality is what? 5, and the degree is the number of attributes, which is 4. You normally have one or more attributes that uniquely identify each row. And in this case, it is the branch number that uniquely identifies each row. You also have often something called foreign keys, which allow you to join the information in 2 different tables. So for example, if I want to know the address where John White works, clearly I can't find it from the staff relation. Nowhere in the staff relation is the address where John White works. But if we know his branch number, then we can go up here to the staff relation and find out that John White works at 22 Deer Road in London. So we call this branch number in this relation a foreign key because you can use it kind of like a pointer to index into another relation and extract information from that relation. Okay? You'll notice too that there is a data type, dates, which you haven't probably been used to before. But in databases, dates are huge, times are huge. So they add another type, which is a date type and a time type. Okay, so that just says what I already told you. Tuple, a row of a relation. An attribute is the name column of a relation. The domain is, domain, the set of allowable values for one or more attributes. That's its type. Domain type. Okay, and a relational database is a collection of normalized relations with distinct relation names. So you might wonder, what do I mean by the word normalized? What it means is that we've eliminated redundancy. Information, so keys have to be duplicated. Notice here that the branch number is duplicated up here in the staff relation. I can't get around the duplication of keys, but I'm not duplicating so-called informational attributes like the street, city, and postcode. So essentially, very informally, normalized means that only keys are duplicated. Okay, so just informally, see if I can somehow, doesn't look that way. What I want to do is write on the screen. I can't do that either, so I'll do it here. Normalized informally means that keys are the only duplicated data. Now, we're going to get to a chapter that talks about normalization, and then we'll define the term more formally, and we'll find out there's various so-called normal forms. But for the time being, informally, it means keys are the only duplicated data. And a relational database is a collection of relations with distinct relation names. Okay, and not a lot to see there, just the domain name is kind of like, just like in C++, you can define enumerated types. So a domain name, a bit like a type name. So branch numbers is a type name, street names kind of like a type names, dates of birth, a type name. And then they have types like character size 15 or a date in a certain range. Or actually another type is monetary values. Often databases need to store monetary information. And it has to be precise. You'd be surprised when you have millions of banking transactions, if you use a float to represent an imprecise amount. So for example, 0.33 cannot be precisely represented using a float or a double. You can make, actually, with millions of transactions, millions of dollars, just because you can't precisely represent 0.33. So they introduced specifically a type that's a monetary type that actually, instead of using a float, uses a different representation so that you can precisely represent 0.33. And that way a bank doesn't. There have actually been white-collar crimes where people have shaved fractions of a penny from banks and made millions of dollars off of it. Pretty clever. Okay, now you will hear a lot of different terminology. So if you are a researcher, you probably like to say relation, tuple, and attribute. If you are a user or a designer of a database, you probably use the words table, row, and column. If you are at Oracle and you are responsible for physically implementing the database, you probably use the terms file, record, and field. So just be aware there's 3 different sets of terms in widespread use. So relation, table, file typically mean the same thing. Tuple, row, and record mean the same thing. Attribute, column, and field typically mean the same thing. Just depends kind of what your role is with regard to the database. And now everyone's favorite part. Why is 311 the prerequisite for this course. Because we got to go through the mathematical definition. And why is that? Because y'all are computer science majors and should know it. So technically, a relation is the Cartesian product of some number of domains. So here's two sets, D1 and D2, with the domains 2 and 4 and 1, 3, and 5. So their Cartesian product is what you see here. A relation would be some proper subset of these 6 tuples. So essentially, a relation is a proper subset of the enumeration of the Cartesian product of some set of domains. Now, mathematically, you can do cool stuff. You can say that my relation consists of all elements in D1 and in D2 such that y is equal to 1. So, if you take the Cartesian product of these two domains, D1 and D2, here are the 6 tuples. If you look for the tuples where y equals 1, you see this tuple here and this tuple here. Hence, you get these 2 tuples in the relation. Or you might ask for a relation where the first element is always twice the second. So x is equal to 2y. There's only one such tuple where x is 2 times y. Every other tuple doesn't have that characteristic. So you can do all kinds of cool stuff mathematically. Do we do any of that cool stuff mathematically in the real world? Of course not. We enumerate our relations. So we just, yes, if we took all possible tuples from the Cartesian product, it would be infinite, right? Because names by themselves, there's an infinite number of names. So we simply enumerate them in practice. But the mathematical definition of a relation, a Cartesian product, there we go, from I equals 1 for these domains. So typically, that is a relation in the mathematical sense, the Cartesian product of some n domains. And then any set of n tuples from this Cartesian product is a relation. Okay. Questions about that? It's not that difficult. Okay. Past the 311 stuff for a moment. We get back to it when we get to the theoretical basis for the manipulation language. So when we talk about a relation schema, remember on Thursday I said that databases have a catalog that users can look at. So that's what users call, that's what so users say catalog, database researchers say relation schema. Actually, database researchers say relational database schema. That's what the catalog is. So a relation schema is the definition for a single relation. So it is the definition of the attribute domain name pairs. Like, just think of a relation schema as a class definition, declaration in a programming language. Variables and their types. Okay, relational database schema, the collection of those relation schemas. Okay, properties of relations. This is what makes them both nice and also limited. So the relation name, distinct from all other relation names, should be pretty obvious. Here's one, though, that's a killer for a lot of people these days. Each cell of a relation contains exactly one atomic value. So you can't have a multi-valued attribute. If you want to have multiple phone numbers, you need one column for each phone number. And that is one of the big drawbacks of the relational model that has caused people to look at NoSQL type databases. Okay, in the real world, there are a lot of multi-valued attributes, such as all the posts that I made on multimedia or social media. Okay, that my posts might be considered a multi-valued attribute. Okay, each attribute has a distinct name. That should be pretty obvious. Within a relation, you can have two attributes with the same names in different relations. Here's another limiting factor for a relational database. The values of an attribute are all from the same domain. So they must all be a date. They must all be an integer. Sometimes that could be an issue because sometimes you want the attribute perhaps to be an image or maybe just a name. So sometimes you might like the value of an attribute to be a Boolean if it false if it doesn't exist, and otherwise something else. You can't do that. They all have to be from the same domain. No duplicate tuples in a relation. So one guarantee of a primary key, remember I said that a primary key is one or more attributes that uniquely identify a tuple. A very simple primary key is the entire tuple, all the attributes in the tuple. Okay, for those of you with a mathematical bent, there's a little bit of a difference. The order of the attributes has no significance, but in math, the order does. So it doesn't matter whether the branch number is here or whether it's at the end of the relation. The two relations would be considered identical. And theoretically, the order of the tuples has no significance. You can put the tuples in any order. In practice, it makes a huge difference with query optimization. We typically sort relations on some attribute. But in theory, the order of the tuples has no significance, meaning if you have two relations, same set of tuples but ordered differently, those two relations would be considered identical. Okay, pretty simple stuff. Now we get into something that's a little harder to wrap your head around. So keys are important for identifying tuples. And we often introduce artificial keys because even attributes that uniquely identify a tuple, they tend to be verbose. So for example, my name. My last name is not unique, but it's verbose. My first name and last name, it turns out, is not unique. I found this out when I Googled me and found an obituary for a Bradley Van der Zanden in Illinois. Not me, but there's another Bradley Van der Zanden out there, which kind of surprised me because Van der Zanden is a rare name. So even first and last name may not be enough to uniquely identify you. And you might go to middle name. Let's just pretend for a moment that first name, middle name, and last name is enough to uniquely identify. That's still a very verbose amount of information. 3 attributes could easily take 30 characters. We don't want to waste, remember keys get duplicated. We don't want to waste that much memory on keys, so we often introduce artificial keys like branch number or staff number. Okay, they're very compact and they don't take up much space. That's why you have social security numbers that are very compact. Okay, so there's some nomenclature. We need to be familiar with it. So we start with a superkey. That is any attribute or set of attributes that uniquely identifies a tuple within a relation. So by definition, all the attributes in a relation are a superkey because we said you cannot have duplicate tuples. So by definition, if you take all the attributes in a tuple, they form a superkey. But we aren't interested in having a key that consists of all the attributes. We would like something a little smaller, so we talk about candidate keys, which are superkeys such that no proper subset is a superkey. So for example, branch number, street, city, and postcode is a superkey, but branch number is a candidate key because by itself, it uniquely identifies the branches. There is a second candidate key here. What might that be? Pardon? So you got to be careful. Maybe, maybe not. It all depends. So this is, you know how Dr. Planck talks about proof by Cosmo, for those of you who have taken his classes? You can't always just look at the example data and infer something. So in this case, you'd have to make sure that we really don't have two branches in the same postcode. If that is the case, then postcode is a candidate key. If not, then it is not a candidate key. What is a guaranteed candidate key, though, since I know that branch number is an artificial key? Pardon? No, I could have two main streets. Main Street is very ubiquitous.
Well, with the actual location, right?
No, I could have one. I could have, by pure dumb luck, 10 Main Street.
163?
Probably not. I'm just, so you might very well, I guess my point is when you do this and you say that something is a primary key, you really have to be, it can't be that there is a 99.99% chance it's unique. It has to be 100%. Even though 163 Main Street is 99.9999% sure to be unique, it's not absolutely unique. So you'd have to be a little careful. Probably street, city, and postcode, the three together, would be the candidate key.
But, I mean, if you're saying that in Main Street, would all three not change that at all?
Well, no, because you can't have 163 Main Street in the same city.
I see.
Right. So, yeah, that's right. You can't have it in the same city, but in two different cities, by pure dumb luck, you might. That was the same point I was making with my first and last name. I thought my first and last name was unique. It turns out that there was someone else named Brad van der Zanden. So the chances of that, there's probably two people out of 300 million. But if we both were employed at the same company, then just using last name and first name would turn out not to be a primary key or candidate key. So you just got to be careful about it. Okay, so candidate key is a super key such that if you remove any attribute from the candidate key, it's no longer a super key. Okay. So they actually talk about uniqueness and irreducibility. It has to, a candidate key must uniquely identify each tuple, and you can't remove any attribute from the candidate key and have that subset uniquely identify it. So it's irreducible. Yes.
So is the point of trying to make the candidate key as small as possible?
Yes. So now we get to alternate keys. So we say that the set, you have a set of candidate keys. Typically you choose as the primary key the one that is the most compact. Okay? So in that staff relation, that artificial key we created, branch number is the most compact. So we choose that. And all the other candidate keys become alternate keys. Yes, Emily?
Basically, what's going on is like, because I remember the side up talked like about primary keys. So if there's a big like circle diagram, it would be primary key, candidate key, super key, and then alternate key right after the side next to primary key. Is that correct?
Let's see. Let me actually go to the Xi book for that diagram, because that's probably something good to look at. By the way, can you all now get to the Xi book?
Yeah.
Good. Okay. So, they did not actually do it. So do you want me to do the Venn diagram? Okay, I'll do the Venn diagram.
Saying if there is a Venn diagram.
Okay, let's see if I can do the Venn diagram. Okay, so we'll start out, and we have some tuples or attributes. We'll call them A, B, C, D, E, and let's make F. Okay, so we have some candidate keys. Candidate keys, you could even have it like this. So let's say those are the 4 candidate keys. Okay? Then we have to, whoops. Just a sec. Unfortunately, this is not making it easy for me to do erasing. Okay, so there's your candidate keys. So now we choose one of them to be our primary, and probably the primary is going to be A because it's just one. Now the remaining 3 that you see there become our alternate keys. So we have 4 candidate keys. From the candidate keys, we choose one and only one to be the primary key.
And the super key would be like if any combination of those up to and including.
Exactly. So let's say, so now let me do another color. So A, B, and C would be a super key, but it's not primary because I can remove B and C to get something smaller. So A, B, C is a super key, but it's not irreducible. It's reducible. You're welcome. Actually, I'll remember this for the future because that's a good way to show it. Okay. We good with our definitions now? Because these get thrown around a lot in relational databases, and everyone uses them, whether they're users or database designers. And the final one is foreign key. The foreign key is a primary key in another relation, and you're using it as a pointer so that you don't have to duplicate that information in the current relation. So for example, rather than duplicate the address information in the staff relation, we put the staff information in a different relation, and then we index into it with this foreign key. And notice that B5 and B5, that way we save space as well. So you can think of a foreign key as though it were a pointer into some other relation, but sometimes it actually can be a pointer into the same relation. As an example, it's not here, but let's say we added a manager column to the staff. So we want to know who your manager is. In that case, your manager would have a staff number. So in that case, staff number would be a foreign key, but it's also in the same relation as it is a primary key. So sometimes that happens where the foreign key happens to point back into the same relation. Is that clear? Okay. Okay. So here is a hotel schema. You're going to use it in homework 1. And it is basically a reservation system. So you have a number of hotels. You have rooms in those hotels with a type like, say, queen, king, maybe suite, and prices for the rooms per night. Then you have your reservations, so when they are staying and what room they're staying in, and then you have your guests. Okay, so can we suggest, so hotel, room, and guest are kind of boring because, I'm sorry, hotel and guest are boring because it's pretty obvious that hotel number and guest number are the primary keys there. Room and booking are more interesting. So what might be a candidate key for room?
Room number and hotel.
Very good. Room number and hotel number. You can't just use room number because 2 hotels might have the same room. In fact, it's quite possible. So room number and hotel number essentially give you the candidate key, and there's no other good candidate key, so that becomes the primary key. Booking is very nice. So can someone suggest a candidate key for booking?
Hotel guest and room number.
So what if a guest books 2 different stays in the same room because they really like that?
You need the dates.
So you're going to have somehow the dates are going to have to show up. Do you need both dates though?
Maybe guest number and date from.
So guest number and date from should probably be enough. That's 1. Okay, we're not going to allow the guest to double book on us. If we prohibit double bookings, then guest number and date from are a candidate key. But there's 3 more. So you found one of the 4.
That have 2 attributes.
How much of a clue do I want to give you? I don't know. Actually, all of them are more than 1 attribute.
Could you do hotel, room, and date from?
Very good. Hotel number, room number, and date from. So we're not, obviously, unless we're a scummy hotel, going to allow hotels to be double booked. Of course, airlines do this all the time, but we would like to think that hotel rooms also aren't double booked. 2 more candidate keys.
Could you just take both of those and replace date from?
Very good. Take both of the candidate keys we've had some so far and replace date from with date to, because date to should also be unique. Again, avoiding double bookings. So there's 4 candidate keys. And this one is a little bit trickier as to which you are going to make the primary key. Most likely you would go with guest number and date from because it's the most compact. And in terms of the queries that you're likely to make, you're probably most likely to make your queries. A guest calls up, says, I'm staying at this room and I want to cancel or extend. So the queries that you're most likely to get are the ones that are guest number and date from. Now, what happens in reality with reservation systems? What do you actually get? You get a booking number. So this is just being done for pedagogical purposes in the homework so that you don't get off with super easy primary keys, that you actually have to make use of some non-artificial primary keys. Okay? Now that you know what the primary keys are, can you identify, are there any foreign keys in the hotel? No. Okay, there's only primary. And I'll give you a hint, there's none in guest either. We do have primary keys in room and booking. I'm sorry, foreign keys in room and booking. So, what is a foreign key in room? Hotel number. And what are the foreign keys in booking? Hotel number, guest number, and room number. So this is a little, though, unusual. Guest number is the foreign key into guest. The foreign key, hotel number and room, hotel number is a foreign key into hotel. Hotel number and room number together are a foreign key into room. So foreign keys, just like primary keys, can consist of more than one attribute. Okay, so there's actually 3 foreign keys in booking. Hotel number into hotel, guest number into guest, hotel number and room number into room. So 3 foreign keys in booking. Okay, good with that?
So foreign keys have to be primary keys in other relations.
Bingo. Foreign keys have to be primary keys in other relations. Always. Okay, next thing about the relation model. It has something called integrity constraints. The first is called null. So it is possible that you could have a value for an attribute, but it's not known. When you do that, you put in null. It simply means the absence of a value. So for example, let's say that we had a viewing relation for our property management firm. So every time a client views a property, the sales representative has to file a viewing report, and that's added to a viewing relation. Let's say that the viewing relation has a comment field where the client might make some comments about the property, such as has mold on the walls. That comment field is optional. The client doesn't have to make a comment. So if the client doesn't make a comment, we put null in the comment field to indicate the absence of a value. Okay? So that means you have, it deals with cases where it's okay to have optional data or exceptional data. It is not the same as 0 or spaces, which are values. If you have 0, that means like $0. Okay? Null in a monetary field simply means we don't have an amount. We don't know what it is. Think of the closing price for a stock. 15 means it closed at 15. Null means we don't have a closing price for it. So using null is an absence of a value. It is not the same as 0. Okay, and if you have a large number of nulls, usually that suggests that you could decompose the relation into 2 smaller relations. We'll talk about that later. It is called normalization. Next type of integrity constraint is that no attribute of a primary key can be null. Makes sense. It uniquely identifies a tuple. Having null in the primary key surely defeats it because it's not helping you to identify a tuple. So you can't have null be a value in an attribute of a primary key. Referential integrity, if a foreign key exists, it's not a dangling pointer. Meaning a foreign key either accesses a legitimate tuple in another relation, or its value is wholly null, meaning all attributes in the foreign key are null. Remember, I said a foreign key is like a pointer. So again, referential integrity simply says you cannot have dangling pointers. That's what referential integrity is. And then we add general constraints. So no staff member may have a salary that exceeds $100,000. Or back here in the hotel schema, no rooms can be double booked. No guests can double book. That's different. Not double booking a hotel room means the hotel can't put two guests in the same room at the same time. Not allowing a guest to double book means the guest can't reserve two or more hotel rooms in either the same hotel or any other hotel at the same time. So those would probably be two similar but different rules, general constraints for the hotel schema. Okay, some other general constraints. Maybe you don't accept bookings you only accept bookings 6 months in the future. This drives my wife crazy. She loves to organize our trips more than a year in advance. But many of the like HomeAway and Airbnb operators don't actually have their calendars out more than a few months. So that might be a constraint that we don't allow bookings, say, more than 6 months in advance. So if you have moral of that story is if you have an Airbnb place to book, I would suggest making your calendar pretty far out so you can get my wife to snaggle it because she often eliminates things if she can't book immediately. Okay. So 4 types of constraints: null, entity, referential, general constraints. Last thing for today, views. We have what are called base relations that are physically stored in the database. We can also have virtual relations, which are not stored in the database, but instead are formed from a query on one or more of the base relations, and these virtual relations are called views. And views are good for both simplifying the database for an end user and for hiding information. So for example, we might like the manager of a branch to be able to see all the information for the staff at that branch, but not for the staff at another branch. So we might create a virtual relation for a branch manager that allows them to see all the staff at that branch, but not at other branches. Or we might want to create a directory from the staff relation that gives each person's name and address, but omits important information like their salary or their date of birth. So the directory would be a virtual relation, which we would get by combining information from the staff and the branch relations. So directory would be a virtual relation. Okay? So it's produced upon request, although we will find out in a couple weeks they might also be cached. So in theory, they are produced upon demand. In practice, they are often cached, and then the cache is updated. Let's see. So views are dynamic, meaning if the underlying base relations change, the view should be automatically updated as well. So I kind of just told you the purpose of views. They provide a security mechanism by hiding parts of the database from certain users. They allow users to access the data in a customized way, such as I want a directory, like a phone directory maybe. So it allows us to access it in a customized way. And it can simplify complex operations on base relations. You'll see that, I think, in the second homework assignment, where sometimes you'd like to, it gets pretty complicated to specify a query. You end up with 5 or 6 base relations. So instead, you in effect create a temporary variable, and then you can do some operations with that temporary variable. Okay. When you update, it's funny. So they claim, in theory, that a virtual relation is produced upon request, but then somehow it exists because you can actually update it. I think this was added later for practical considerations for what happens when you cache your relations. So if you update the base relation, you should immediately update the view. In practice, we allow views to be updated. So we might update the directory. If we do that, we would like those changes to the directory to be made to the underlying base relation. So for example, if we update my address in the directory to be 1678 Dune Avenue, then I would like my address in the staff relation to also be updated. Okay, but there's restrictions on the types of modifications you can make to a view. You're only allowed to update a view if the query involves a single base relation. So the example I just gave you was bogus because the directory would be formed from both the staff and the branch relation. Because that involves 2 different base relations, you actually could not update the directory. Yes. You do or don't have a question? Oh, don't have. Okay, no worries. It's going to be a lot easier when we get into SQL. We will see more clearly why it can be hard to update a view if it has multiple base relations. Things can get ambiguous. And something else we haven't really discussed is that the relational model also in the query language, in the direct manipulation language, allows for certain aggregation operations. So you can find the maximum value in a column. You can find the minimum value in the column. You can take the average value of a column. And if the views columns are formed from an aggregation operation, then you can't update the views. So for example, let's say we have a view that shows the average salary at each branch. And now let's say I want to do some cost cutting because I'm the Grinch, and I see that the salaries at some branch average 43,000, and I say change that average to 40,000. How do I update the base relation? What I have to do in the base relation is change a whole bunch of staff salaries so that the new average is 40,000. So the problem with allowing an update when things have been aggregated is how do you actually map that change into multiple tuples that have been aggregated? If I say change the average from 43,000 to 40,000, well, whose salary gets modified? In fact, a whole bunch of salaries will have to be modified to reduce the salary to 40,000. Okay? So, that is it for the day. Any questions?
When is the first thing due?
First quiz is due Thursday.
I'm sorry, I meant the first assignment.
Oh, the first assignment isn't even assigned yet. It's due on the first assignment will not be assigned until Thursday, and it is due a week from Thursday. So don't worry about the assignment yet. It's not. Pardon? The quiz should appear at 2 o'clock. Yeah, so the quiz won't appear until class ends, so it always appears 10 minutes after the end of class.